Quantum computing? Man, it feels like it's just everywhere these days, right? It's promising to change, well, everything. But what's the real story behind all the headlines? That's what we're going to do today. We're going to cut right through all that noise and lay out the actual real-deal roadmap. A step-by-step journey that'll show you exactly where we've been, where we are right now, and where this whole thing is headed. All right, let's get into it.
So, this is the big one, isn't it? The question that's probably on your mind too. You see all these headlines about breakthroughs, stuff that sounds like it's straight out of science fiction. But it's so hard to tell what's a real milestone and what's just, a flashy press release. Are we looking at a genuine revolution here, or are we all just caught up in one massive hype cycle? And look, if you're confused, you're not alone. It's totally understandable.
And this right here, this is the key to unlocking this whole thing. The source material for this explainer makes a really brilliant point. See, quantum computing isn't one giant leap. It's more like a ladder. It's a series of different, totally required levels. And here's the kicker. You absolutely cannot skip them. All that hype we were just talking about, it basically comes from people mixing up the amazing promises from the top of the ladder with the reality of where we are today, which is much further down.
So that's our mission today. To separate that hype from the reality, we are going to build this roadmap together, one level at a time. The goal here is simple, to give you total clarity by walking through every single level, starting at the very, very beginning with pure physics and going all the way to those world-changing apps we hear about.
All right, so let's rewind. Let's go way, way back to the very beginning. We're talking level 0 here. This is the pure physics part of the story, long before anyone even had the faintest idea of a quantum computer. Yeah, we have to go all the way back to the start of the 20th century. So for the better part of 100 years, this had nothing to do with building a machine. It was all about just trying to understand the universe. You had scientists grappling with these totally bizarre new rules, things like superposition and entanglement, and slowly realizing that, the world on a quantum level, it just plays by a completely different set of rules.
And that was really the big takeaway from these first couple of levels. This huge discovery that quantum information is just fundamentally different from the classical bits. The simple ones and zeros that power our entire digital world. But here's the thing. At this point, it was a pretty incredible solution with absolutely no problem to solve.
And this is such a great way to think about it. It's like, imagine if you discovered all the physics of semiconductors back in the 1800s. You'd have this incredible, game-changing knowledge, but the idea of a transistor or a microchip, it wouldn't even be a dream yet. That's exactly the spot the world was in with quantum mechanics.
Okay, so that brings us to the next crucial phase on our roadmap. This is the moment where that pure scientific curiosity starts to morph into a real, actual computational idea. This is where the story really pivots from just physics to computer science. And on this level, level 2, there were two critical sparks that basically changed everything. First up, you have the legendary physicist Richard Feynman. He points out something that seems obvious in hindsight. If you want to simulate a quantum system accurately, well, you're probably going to need a quantum system to do it. Then, about 13 years later, Peter Shor delivers the killer app. He comes up with an algorithm that shows how a quantum computer could, at least in theory, completely shatter most of the encryption we use today. And just like that, boom, there it was. For the first time ever, we had a really compelling, practical, and honestly, a world-changing reason to actually try and build one of these seemingly impossible machines. The motivation? It was now crystal clear.
But hold on. Before anyone could even think about connecting a single wire, the scientists had to build the entire computer on paper. This is level 3. They had to come up with a mathematical definition for a qubit. They had to design the quantum gates that would be the basic logic operations. And, this is so important, they had to figure out the theory for how to fix all the errors they knew would constantly mess up these super delicate systems.
And again, the analogy here is just perfect. It's like designing the logic gates in the whole architecture for a CPU before you've even thought about building a factory. We've officially moved from discovering a law of nature to having the complete, theoretical blueprints for a brand new kind of machine.
Okay, so we've got the theory, we've got the motivation. Now comes the monumentally difficult part, actually trying to build one of these things in the real world. And that brings us to level 4. This is where physicists and engineers roll up their sleeves and try to create actual physical qubits. And as you can see, it wasn't like there was one obvious path forward. You had teams trapping individual ions, others building tiny superconducting circuits, some using particles of light. It was this total explosion of different experimental hardware, with everyone trying to figure out how to tame the quantum world.
This comparison to early vacuum tubes is so spot on. It really gets to the heart of this stage. I mean, these first qubits, they were huge, they were clunky, they were unbelievably fragile. They proved the basic idea could work, but man, they were sensitive to the slightest little disturbance from the outside world and couldn't hold their quantum state for very long at all.
Which brings us pretty much to today. We are now firmly in what everyone calls the NISQ era. That stands for Noisy Intermediate Scale Quantum. And what that means is we have machines with, dozens or even over 100 qubits. We can run some small programs on them, but that N for noisy, that is the key word. Errors are everywhere, they still dominate everything we do, and they're what's stopping us from doing any truly useful computation, for now.
So, okay, after all this history, all this theory, all this ridiculously hard hardware development, what's the end game? What is the actual payoff that we're all working towards?
This is the holy grail. Level 7, the fault-tolerant quantum computer. And the big idea here is to use all that error correction theory we talked about earlier to take thousands, maybe even millions, of the messy, noisy physical qubits we have today and bundle them together to create just one single, near-perfect, super reliable logical qubit. This is what people call the Pentium moment for quantum. It's the point where the hardware finally gets good enough to do real complex work. And it's only after we reach that fault-tolerant stage that we can finally climb to level 8, the real-world applications we're always hearing about. But look at how specific these applications are. We're talking about things like simulating molecules to invent new drugs or materials, using Shor's algorithm to break codes, and simulating complex physics. These aren't random problems. They're the problems where quantum mechanics is literally the native language.
And this part is just as important as what they are for. Let's be super clear. A quantum computer is not going to replace your laptop. It's not for running Windows, it's not for browsing the internet, it's not for training most of the AI models out there. Think of it as a highly specialized tool, like a supercomputer, designed for a very narrow but incredibly difficult class of problems. All right, so we've walked the entire roadmap from level 0 all the way up to level 8. Now it's time to tie it all together with what is probably the single most important secret you need to know about all this.
And it's this simple. You cannot jump levels. It's impossible. You can't get those amazing level 8 applications, like designing new medicines, by using the noisy level 5 or 6 hardware we have today. All that hype and confusion we talked about at the beginning, it's created almost entirely when people mix these levels up, when they promise you the view from the top of the ladder while we're all still busy building the middle rungs. So why are we going to all this trouble? What's the big advantage? Look, it's not just about being faster, like a Ferrari is faster than a regular car. It's about tackling a completely different kind of problem. There are certain problems where, on a classical computer, the difficulty just explodes. It scales exponentially. For every little bit you add, it gets twice as hard. A quantum computer has the potential to turn that impossible exponential curve into a much more manageable polynomial one. It changes the nature of the problem itself. And this one line really just sums up the entire field. The whole reason for this massive, multi-decade, multi-billion-dollar quest is this. Our classical computers, no matter how powerful they get, just cannot efficiently handle the complexity of entangled quantum states. They don't speak the language. So if you want to simulate nature accurately, you need a computer that's built using nature's own weird and wonderful rules. So there you have it, the real quantum roadmap. It's not some big mystery, right? It's actually a pretty clear, logical progression of levels that build on each other. And that leaves us with the one big question that nobody, and I mean nobody, can answer for sure. Just how fast are we going to travel along this road? How quickly will we climb from the noisy machines we have today to the truly powerful, fault-tolerant computers of tomorrow? That is the grand challenge.